Physics is about measurements. But what is measurement? Measurement is the comparison of a known quantity and an unknown quantity of the same kind. Suppose I have a book and a few stones with known mass. Now I want to know the mass of my book. How can I find it? I can try to balance a few stones and the book. So what am I exactly doing is I'm comparing my book's weight, mass, and the mass of the stones. So I'm comparing a known quantity and an unknown quantity of the same kind, which here is mass. Okay, but what do we measure? We measure physical quantities. Physical quantities are mass, velocity, force, acceleration, luminous intensity, and so on. We have classified physical quantities into fundamental quantities or basic quantities and derived quantities. Fundamental quantities are length, mass, time, luminous intensity, thermodynamic temperature, electric current, and amount of substance. And derived quantities are quantities which are a combination of these basic quantities. Now look in this table. You can see the basic quantities and their definitions. These fundamental quantities are not actually fundamental. We've assumed them to be fundamental. We could have assumed that time is a derived quantity and speed or velocity is a fundamental quantity. It is all our convention. But it will be good if we think about why we assume these quantities as fundamental. Feel free to discuss about it in the comments. We have different units for different basic quantities. But what is a unit? It is something which is the same for everyone and available to everyone. For example, I want to tell my friend the distance between my house and his house. Then I can tell him in many ways. I can tell that if he keeps 50,000 oranges in a line from my house to his house, then that far it is. Or I can tell that if he rolls a ball in a straight line from his house to my house, then in 5,000 rounds it will reach my house. So what we are doing here is expressing the distance or length. But the problem here is that the size of different oranges and balls are different. So a unit must be the same for everyone, and it must be available to everyone. Nowadays, we have the International System of Units, which uses the SI units as the standard units. For length, it is meter. For mass, it is kilogram. For time, it is second. For temperature, it is Kelvin. For the amount of substance, it is mole. For electric current, it is ampere. And for luminous intensity, it is candela. In 1792, the newborn Republic of France established a new system of weights and measures. Its cornerstone was the meter, which was defined as 1/10 millionth of the distance between the North Pole and the equator. Later, for practical reasons, this definition was abandoned. They defined meter as the distance between two fine lines engraved near the end of a platinum iridium bar, which is called the standard meter bar, which is kept at the International Bureau of Weights and Measures near Paris. Nowadays, if you look at the definition of meter, then it says that a meter is equal to the distance traveled by light in vacuum in 1/299,792,458 of a second. The speed of light in vacuum is constant for all observers, making it an ideal way of defining units. Now we have our SI units to express different fundamental quantities. But suppose we want to express the mass of the sun using our SI unit of mass, which is kilogram, then it will look like this. And if we represent the mass of an electron, it will look like this. So these numbers look very complicated. So we use SI prefix to simplify these numbers, or we use scientific notation to make these numbers look simple. In scientific notation, we have any number between 1 and 10 or equal to 1, which is multiplied by a 10 raised to an integer. If you write the mass of the sun using the scientific notation, then it will look like this. Now it looks quite simple. Now in our day-to-day life, we do not say that my hometown is 5 into 10 raised to 5 meters. So we can use SI prefix to simplify our daily communications. We know that 5 into 10 raised to 5 meters is equal to 5 into 10 raised to 2 times 10 raised to 3 meters, or 5 into 10 raised to 2 kilometers, or simply 500 kilometers. Here's the list of SI prefix and their relations with the SI units. Now we will look at some examples. If we write 5 into 10 raised to 8 meters using kilometer, then we will first need to isolate 1 kilometer from 5 into 10 raised to 8 meters. We know that 10 raised to 3 meters is equal to 1 kilometer. So we can split 5 into 10 raised to 8 meters into 5 into 10 raised to 5 into 10 raised to 3 meters, or 5 into 10 raised to 5 kilometers, or simply 500,000 kilometers. Here we have converted the meter into kilometer, or we have converted units. There is another way to convert units, and I am going to show it to you now. Suppose we want to find the number of minutes in a week, or we want to convert the week into minutes, and we also know that if we multiply any number by 1, then we will get the number itself. Now we know that 60 minutes is equal to 1 hour. So we will divide 60 minutes by 1 hour, which will give us 1. Now using this logic, we will convert the units. Now look at this expression, which simplifies to the number of minutes in a week. Look at it carefully and you can see that the fractions here are equal to 1. Now we can cancel out the units and the numbers and simplify the expression and get the number of minutes in a week. Now look at the SI prefix here. In the metric system of units, we have meter for length, kilogram for mass, and seconds for time. In centimeter gram second system or CGS system, we have centimeter for length, gram for mass, and seconds for time. In FPS system, we have a foot for length, pound for mass, and seconds for time. Maybe you are familiar with the relationship between CGS and metric system of units, but then also I will give the relationship between the metric system and the CGS system and the FPS system here. Just look at the relationships of the units given here. Now let us look at some derived quantities. Force is a derived quantity. Now we know that force is equal to mass times acceleration, or rate of change of momentum. If you don't know this, then no problem, as we will visit this in the future. Some basic quantities have a dimension. Yes, not every basic quantity has a dimension. We have radians, which is equal to the length of the arc divided by the radius and is a measure of angle. You can see that this is dimensionless. We even have a solid angle, which is the measure of a three-dimensional angle. We can write a derived quantity as a combination of the basic quantities which have dimension. When we write a physics equation which is simplified into a combination of these basic quantities, then we call it a dimensional formula. Suppose we want to write F equals ma as a dimensional formula. Then it will be somewhat like this. Using this dimensional formula, you can even derive different physics equations. Suppose we want to derive the formula for the time period of a pendulum when we neglect the air resistance. We know that the time period is a basic quantity, which is time. We also know that acceleration is velocity per unit time, or displacement by time squared. So we can write time squared as length by acceleration. So time is root over length by acceleration dimensionally. So time period is k times root over length by acceleration, where k is the constant, length is the length of the pendulum, and acceleration here is the acceleration due to gravity. We can even convert units using dimensional formulae. Suppose we have a bucket of water and the water pressure at the bottom is 10 pascals or 10 newtons per meter squared. Now suppose I want to represent this in the CGS system of units. First, we will try to figure out the ratio between the metric system and the CGS system of units for pressure. Now the dimensional formula of pressure is ml raised to minus 1 t raised to minus 2. So the dimensional formula of pressure in the metric system is 1 kg into 1 meter raised to minus 1 into 1 second raised to minus 2. So the dimensional formula of pressure in the CGS system is 1 gram into 1 centimeter raised to minus 1 into 1 second raised to minus 2. Now the ratio between the metric system and the CGS system will be equal to the following. Now we can find the value of 10 pascals in CGS system of units in the following manner. But there are some disadvantages of dimensional formulas. When we divide a physics formula using dimensions, we cannot know the constant value in the equation. For the time period of a pendulum, we see that it is equal to k times root over length by g, but we don't know the value of the constant k using dimensions. The constant is 2 pi, where pi is the ratio of circumference and diameter of a circle in a Euclidean plane. And if we want to derive a formula using dimensions, we need to know the dimensional formula of derived quantity. For example, if we look at the famous equation E equals mc squared, then we cannot prove it using dimensions unless we know the dimension of energy, which is ml raised to 2 t raised to minus 2. So we cannot always use dimensions for deriving formulas or proving them. Now let us talk about another derived quantity. Density is a derived quantity, which tells us how dense or how close each particle of matter is to each other. More the number of particles of matter present in the substance, the denser the object will be. More the volume of the object, less dense the object will be. So density is simply mass divided by volume. Now if we throw a solid object of density 750 kilograms per meter cube into water at room temperature, will the object float on the surface of water? Note that the density of water is 1000 kilograms per meter cubes at 1 atmospheric pressure and room temperature. I think most of you will know the answer. The object will float on the surface of water because the object is less dense than water. The relative density of an object is the ratio of the object's density and the density of water. If the object's relative density is less than 1, then the object will float on the surface of water, or it will float, or else it will sink to the bottom. Because if the relative density is more than 1, it means the object is denser than water. Now let us discuss about liquefaction and density. Due to earthquakes, the soil can undergo liquefaction. This will cause the objects on the soil to sink in it, just like in quicksand. Now let us calculate the density in which soil will undergo liquefaction. We know that there are countless gaps between each soil particle. Now, let the ratio between the volume of gaps and the volume of each grain of soil equal to E. When E exceeds a critical value of 0.8, then liquefaction can occur due to earthquakes. Now, at what density of soil will it undergo liquefaction? First of all, we know that the density of soil equals to the mass of soil and the total volume. Now we know that total volume is volume of each grain plus the volume of empty space. Now solving for volume of grains in this equation will give us the following. Now substituting this to this equation with further simplifications will give us the following. Now we know that soil is mostly made up of silicon dioxide. So the mass of soil will be density of silicon dioxide times the volume of each grain of soil. Now substituting all this to our final equation with further simplification gives us the following. Now substituting for the density of silicon dioxide in this equation and the critical value of E, and this equation and solving this equation gives us the following. So at this density of soil, after an earthquake, a large building can sink several meters into the soil. Now, if you want some problems regarding all this, then I am giving a few problems along with the solutions regarding this topic. But it would be better if you solve problems from a physics book. In this video, I discussed the introduction of physics and tried not to miss anything. And I hope you enjoyed the video, and thank you.